discuss certain parts of analysis of variance. Today's contents are: first we will introduce with an example, and then we will see that how one factor experimental data can be represented in tabular form. Then we will discuss the partitioning of data observations for single factor ANOVA, and also the models for the data, and then how to decompose the sum of squares into treatment effects, error effects, and that same thing with an example with data we will explain. So, let us start with the same example what we have seen in earlier lectures. Suppose the engineer is interested to study the methods of improving the ability to detect targets on a radar scope. Two factors considered to be important are ground clutter and type of filter. Response variable is the intensity level at the time of detection, that is what is measured, and in this example we are considering only one factor, that is ground clutter, which is having three levels: low, medium and high. For the time being, like earlier in earlier lectures, we assume that this data comes from an experiment, that is one factor experiment, and ground clutter level at low, medium and high, and there are 8 observations or 8 replicates against each of the 3 factorial settings or 3 treatment levels. So, I also explained in earlier lectures that a use of box plot. So, from the box plot we wanted to know whether there is difference in means and medians when the factor level changes from level 1 to level 2 to level 3. In fact, in this box plot the median lines are given, these horizontal lines, middle lines are median. So, there can be somewhere mean here and mean here. So, from this plot it is visible that there is difference in mean response from when you observe with ground clutter level low to medium to high. But this is a visual one only, just, and it all depends on the scale you are using. So, it can give you, okay, you go for some kind of other analysis, but it will not clearly give you that whether the difference is statistically significant or not. And in the right hand side a scatter diagram is shown. This is just to see that how the data behaves in terms of the relation between these two variables. Scatter plot is an useful one to talk about the relation, but from the scatter plot again it all again depends on the response measurement, that the scale of the figure. So, here also from here we are not able to find any significant, we are not able to find out much difference between the mean labels. Okay. So, essentially what happened then, that if there is one factor experiment, let the factor is A, denoted by A, then this factor has say A labels, let A mean level 1, level 2, like A labels. So, we say I from 1 to A, and then against each level you have n replications, j equal to 1 to n, and each of the responses now can be denoted by Yij. What does it mean? This is the response for the jth observations when experiment done for ith treatment level. Ith treatment level. What I mean to say, your factor A is having level 1, level 2, like level I, similarly suppose level A, and there is replicate that denoted by j equal to 1, 2, 3, like j, like n. So, then the general observation is Yij. So, ith level jth observation, that is what I have written here. Okay. And this is what is the representation of data when you do experiment for one factor experiment again, which is having A levels, each having n replications. Then your data set will be Y11, Y12, Y13. So, like Y1j, like Y1n. This is Y21, this is Y22, Y23, Y2j, Y2n, then Yi1, Yi2, Yi3, Yij, Yin. In the same manner, Ya1, Ya2, Ya3, Yaj, Yan. So, that means the number of observations, total observations, if I say equal to n, then this is nothing but A level times n, A levels times n. Okay. Now, one factor experimental data. So, let us see the slides. So, you see this is data representation for one factor experiment. The what I have given in this slide, this is nothing but data representation for one factor experiment. You may be interested in total here, you may be interested in average across each level here. So, by total, what I mean to say, suppose the ith total, you can write down yi dot. So, then first row total is y1 dot, y2 dot, like here ya dot. If you want to get average, then you write y1 dot average, y2 dot average, yi dot average, ya dot average. And then someone may be interested to know the total of all the observations y dot dot and grand average y dot dot bar. Okay. So, you know how to compute average, how to make total, all those things. So, this is what is there, but we will proceed further. So, I want to go to the slide. So, in general there are A levels of the factor, that is A treatments, and n replicates, you see n replicates, and you all know this is a random experiment. So, how to make randomization, that also we have discussed in first few lectures. So, this is a complete randomized design case. I told you n total runs, and here we can consider two kinds of models here, a fixed effect, if it means the treatment fixed treatment, otherwise random treatment, random effects. So, we will discuss later. Okay. So, why we have done this experiment? We have done this, or we will be doing this experiment to know that whether the means across different levels differ or not. That is what we want to test. It will be a hypothesis testing case, where you have more than 2 levels or 2 treatments, and you want to test whether the mean response across the different treatments are equal or not. So, equality of treatment means across various treatment levels. Okay. So, with this we will now formally define the single factor model. So, single factor model will be defined like this: y I j equal to mu plus mu I, okay, mu plus, I will write like this, tau I plus epsilon I. This is more general one. So, mu plus tau I is basically mu I, that also we can write, but okay, we will start with this mu plus tau I. So, what is the yij? This is a general observation. What does it mean by general observation? Means the response value for the jth observation and when on ith experiment level, or on the experiment of ith level of factor A. Then what is this mu? This is known as grand mean. What is this tau I? Tau I is because you have one factor, the factor effect. Otherwise, we can say the treatment effects. What is this portion? This is the random error part. So, if tau I is fixed, it has a particular effect that is constant, then this model will be known as fixed effect model. Fixed effect model. Okay. Now, this in this diagram, so what is I equal to 1 to A, what is J equal to 1 to N. This is our model, that is one factor ANOVA, single factor ANOVA model. Okay. So, here very important concept is this is the random error. This random error means it has certain distribution. So, epsilon I j will be normally distributed with 0 mean and sigma I square variability if the variance across the different levels, we have A with 1, 2 like A levels. If the variance of y when experiment done is done at the factor level A at level 1, then the variance is suppose sigma 1 square, then this will be sigma 2 square and this will be sigma A square, or ith case this will be sigma I square, then we will write like this. Okay. Suppose we do one kind of assumption here that okay, that sigma 1 square equal to sigma 2 square equal to sigma I square equal to sigma square, then we can write that this epsilon I j is 0 sigma square. That means the response values y values across different levels. So, level 1 n observation, level 2 another n observation. If you have substantially large number of experimental data, you will find that from the data the variability across these values, across these values, across these values, across these values will remain same or similar, almost equal. Then we can assume that variability across different of y across different level is equal, that is sigma square. Then this error term follows normal distribution with mean 0 and sigma square variance. This is a very important assumption. Later on when I talk about assumption, we will come back to this, but this is known as homoscedasticity assumption, scedasticity. Okay. Those things we will discuss later on. So, as I told you that mu plus mu I, so you can also write that y I j equal to mu I plus epsilon I j. So, then what is mu I j? Mu I equal to mu plus tau I. So, this one is known as partitioning also. You see that the observation, a particular experimental run, y of values what you got, you partition into grand mean, into fixed factor effect plus random error. So, it is partitioned into three components: overall mean, factor effect and error. So, overall mean plus factor effect is giving you the mean at each level. So, mean at this level is mu 1, mean at second level is mu 2, mean at I level is mu I. So, then what we are saying that this tau I equal to mu I minus mu. You see from here tau I equal to mu. So, mu I is mean at each of y at each level, ith level mu I. If I equal to 1, this is the first level. Okay. So, this is what is our model data representation and model. And here interestingly what is happening, suppose I plot the data across this side y, suppose this is my mean, suppose you are talking about these are the treatments, our treatment is A. So, at different level, first level, second level, like here it is ith level, so maybe 8th level. So, everywhere there will be a mu. So, first level mean may be here which is mu 1, second level mean may be here which is mu 2, ith level mean may be here which is mu I, 8th level mean may be here which is mu A. So, these are the mean at of y at different level, and then average or mean of the means is the grand mean. Then what is the effect? Effect is the difference between these two. This is tau 1. So, this one is tau 2, this is tau 3, tau I, and this one will be tau of A. So, it is nothing but difference between individual level mean and the grand mean. Again grand mean can be computed from the individual level means, like grand mean is sum total of mu I by A, I equal to 1 to A. Okay. So, this restriction or constraint, this leads to sum of tau I equal to 0, I equal to 1 to A, means this plus this plus this plus this, if you do you will get it 0. Okay. Obviously, we are considering equal sample size that is n across all levels of A. When you are doing experiment, they are considering equal. Okay. Otherwise, what will happen? If the sample size varies, sample size is n I equal to 1 to A, then it will be I equal to 1 to A, n I tau I, this will become 0. Okay. So, this is the restriction, and this help us in doing many things. Now, come back to the slide. So, in fixed effect model, we consider that tau I is fixed. You just see that we think mu as and then in the random effect model, you see here tau I are random variables and knowledge about particular ones investigated is relatively useless. Instead, hypothesis is tested about the variability of tau I. So, you do not have fixed value for tau I, it's a random one, it's a random variable. So, instead of mean you will be interested in the variability of tau I. Okay. But ANOVA is analysis of variance, even though it is analysis, it is named as analysis of variance, but it actually tests the equality of population means. Okay. So, that means when you say y ANOVA model, you have to say y I j equal to mu plus tau I plus epsilon I j, and then definitely you will be saying tau I equal to 0, I equal to 1 to a, or I equal to 1 to a n I tau I equal to 0. This you can also write like this, y I j equal to mu I plus epsilon I j, and epsilon I j is normally distributed 0 and sigma square. That is what we have learned so far. Okay. So, now come to the point that you have done the experiment. Once you have done the experiment, you will get this kind of data. So, the row of interest for us now is this row, ith row, to do some kind of maneuver, and the very important observation y I j, which is basically observed. So, if you say that okay, y I j is this, from the population point of view, when experiment is not done, this is what is the model. So, once experiments is done, you will get some data y I j. Then what you require? You require the mean value, that will be y dot dot bar. I have given you the grand mean, this is my grand mean, and these are individual means or averages. So, instead of mean you can write grand average also and individual level average. So, this one will be estimated by this, and this tau I will be basically y I dot bar minus y dot dot. Why? Because we know mu I equal to mu plus tau I, and tau I equal to this. So, mu I estimate is mu I dot bar, mu's estimate is this. So, plus this epsilon I j. So, y I j epsilon I j. Now, you may write this one as epsilon I j, you may write y I j minus y I dot bar. First mu corresponding to this, tau I corresponding to this, epsilon I j corresponding to this. Is right hand, both side, left hand side, right hand side equal, y dot dot bar, this will be cancelled, this will be cancelled, y I j equal to y I j. So, this is known as partitioning the observation. So, what we have done here then? We have written y I j equal to y dot dot bar plus y I dot bar minus dot dot bar plus y I j minus y I dot bar. So, one single general observation is partitioned into grand average, treatment effect, error. So, from here we will derive a concept called sum square, that is known as SS. So, what you do? You just write down y I j minus y dot dot bar, left hand side, then right hand side will be y I dot bar minus y dot dot bar plus y I j minus y I dot bar. If you take square, then you have to square it, and then take summation, then you sum here. So, as I and j both are there. So, I stand from change from 1 to a, j stands from 1 to n. Suppose I will write j equal to 1 to n here. So, you write j equal to 1 to n here. Similarly, another summing will be there, not only across, not suppose if I put 1 j equal to 1 to n, that means you are summing up y 1 plus I 1 plus y I 2 plus y I 3 like this. So, you are subtracting by y bar and then making square and summing up. So, if you make, then there is another portion is 1 to a. So, that also you sum up. So, I equal to 1 to a, then another sum I equal to 1 to a. What will happen if you expand this? Now, see the slides. See what I have written here, I equal to 1 to a, j equal to this square. Now, this one when you take double sum, then you see you are doing this, and finally, this portion left hand side is becoming n times I equal to 1 to a y I dot minus y double bar square plus this, here double sum is there. So, this one, when each of the observations are subtracted by their grand mean and taken square and make sum of, this is the sum square total. This is sum square total, this is total. Now, here what is happening, each of the treatment means are subtracted from the grand means or grand average. Each of the treatment average is subtracted from the grand average, and then you have taken their sum, a square, and sum across all the levels, and then this one is nothing but sum square treatment and rest is sum square error. Okay. So, from here to here is a very simple one. This quantity remains valid, this quantity remains valid, and this quantity becomes 0, because j equal to 1 to n. If you sum up here, you will find out that this quantity will become 0. So, one quantity, this y I this y j, one of these two will be, this one will be, I think this one will become 0, and ultimately this is a simple one, it is not a big one, a big issue, because if you write j equal to 1 to n, then this will be n y bar square will be there, and this also will be n y bar square. This n y bar minus n y bar, that will become vanish, that will vanish, and you will be having total sum square equal to treatment sum square equal to individual sum square. So, what you are getting then? You will get SST equal to double sum y I j minus y dot bar square. You will get treatment equal to n, one sum I equal to 1 to a y I dot bar minus y dot bar square, and there will be SS error, again double sum, then this is nothing but y I j minus y dot bar this square. Okay. So, interestingly, then what we have achieved, SST equal to SS treatment plus SS error. This is known as sum square, decomposition of sum squares, decomposition of sum squares. Okay. So, we will see the one example here, and ultimately in ANOVA, as I told you that in ANOVA we test null hypothesis, that mu 1 equal to mu 2 equal to mu a, and alternate hypothesis is mu I not equal to mu k for at least one pair, mu 1, mu 2, mu 3 like this. For at least one pair, there is a difference. This. So, this one we test, this is the hypothesis. What hypothesis we test? What are the hypothesis? Null hypothesis is all means are equal, alternate hypothesis is at least one pair is not equal. So, that is H1, H0 and H1 here. Okay. So, we will see how the sum square decomposition is taken place. You just see this slide. Here we have 8 number of observations and you find out the total and their average, second average, like this average, this is grand average. We use this formula and we got that SSE equal to 1632.25, SS treatment is coming 353.08. This is nothing but using this formula only. So, what is Yij? Suppose 90 minus grand average 95.33, this square is this square 90 minus 95 point like this, then 86 minus this. So, make it and square it and this one, this square. So, every observations will be subtracted by their respective, by the grand mean, grand average, and then square it, and then when you make the total you will get this value. Okay, you will get this value. Now, for the treatment, how many treatments are there? There are 1, 2, 3 treatments. So, what is this? 3 treatment, treatment average minus grand average, its square, then second treatment average, grand average square, third treatment average, grand average square, then take the sum, you will get SS treatment like this. Okay. So, essentially what we basically calculate, we calculate that SS treatment and SS total, and then SS error will be the SS treatment minus SS total, and accordingly you will get the values. Second one is like this, another here what happened, this is the first example what I have given you in the first from the first class onwards we have given it. This is the second example. Second example is here an engineering interested in investigating the relationship between RF power setting and each rate for this tool, and here basically response variable is the each rate, and you are using different power 160 watt, 180 watt, 200 watt and 220, that means 4 levels. So, there are 5 replications and this is what are the experimental data coming, and then this is the total and average. Now, find out SS error, SS total treatment and SS total. Okay. So, here let me give you tell you that there is some typographical mistake. So, please follow this. When you are talking about SST, that means each of the observation is subtracted by the grand average and then that difference is taking sum, taken squared and then overall sum. When you are talking about SS treatment, every label average is subtracted from the grand average, then there that difference is squared and then using this you are getting this. And when you are talking about SS error, that means you are every average value Yij, sorry Yij, not Yij bar, Yij, every observation is subtracted from their respective label average, and then this one is summed up. What does it mean? Here 575 minus 551.2, then 542 minus 551.2. So, in the label 1 all these observations are subtracted by the respective average and then that one is squared and summed up. So, the similarly there this one, this, that 4 different levels, 4 into 5 20 observations will be summed up using this formula will be summed up and you will be getting SS error. Okay. So, what is the mistake here, typographical mistake here is there is a bar here, yi dot bar. Okay. So, if you here it is okay, yi dot bar minus this, the 3 levels, here one bar is missing, please put that bar, yi dot bar. Okay. So, I hope the calculations are correct, it is done in the Excel. If there is a mistake, please mention in the discussion forum, please check. So, this is what is decomposition of sum squares. So, I hope that you understand. So, what we have discussed? We have discussed one factor CRD, complete randomized design. Then we have seen that data representation in tabular form. Then what we have seen that the ANOVA model. Then we have seen that that is the effect model. This is what is effect model, or you can write this one as mu I plus epsilon I j. This is mean model. And then here also we have said that this error is normally distributed with sigma square, 0 sigma square. And then we have seen that a general observation, how it will be partitioned to different component. From there we have seen that how the sum square total is partitioned into sum square treatment plus sum square error, and we have given a general formula for calculation of this equal to double sum y I j minus y dot dot bar square equal to n I equal to 1 to a y I dot bar minus I double dot square plus here it will be double sum y I j minus y I dot bar square, and here it is j equal to 1 to n, I equal to 1 to a, I equal to 1 to a, j equal to 1 to n. Okay, and then I have given you two example. One is that is radar scope example, where ground collateral level A has 3 levels, and another one is the each rate each rate example, where basically some power is used 160, 180, 200 and 220. So, that means the factor A has 4 levels, 1, 2, 3 and 4 levels are there. And then how to compute the different things, SST, it is given to you. Please practice it. Thank you very much. And I have taken all those those things from the book Design Analysis of Experiment by D.C. Montgomery, Wiley 8th edition. Thank you very much. We will go to next, we will see next lecture now.